Hello everyone, my name is Zhang Hanyang and I'm from Tianjin University. I'm glad to have a chance to share my work here. The title of my talk is Optimization of Validation Process for PEMFC 3-dimensional plus 1-dimensional model using a data-driven surrogate model. In this study, we developed a method to simplify the model validation process by combining the physical model with artificial intelligence. My work mainly consists of the following four parts: background, methods, results and discussion, and conclusion. As we all know, proton exchange membrane fuel cell is a clean and efficient energy conversion device. It converts chemical energy into electricity through electrochemical reactions, and the product contains only water. The picture shows the working mechanism of the PEM fuel cell. The PEM usually consists of bipolar plate, gas diffusion layer, microprocess layer, catalytic layer, and the proton exchange membrane. At the anode, hydrogen splits into protons and electrons. The protons pass through the membrane and travel to the cathode. On the contrary, the electrons travel through an external circuit to the cathode. At the same time, oxygen reacts with the protons and the electrons, producing water and heat. Three-dimensional plus one-dimensional model is one of the useful simulation tools to explore the water and heat management in PEM fuel cell. It gave consideration to both model accuracy and calculation efficiency. It is widely considered as the most suitable model to simulate the large-scale flow fields in PEM fuel cell. Model validation is the essential part of all the simulation work. The same is true for the three-dimensional plus one-dimensional model. The accuracy of validation is related to the subsequent calculation. However, in order to fit the experimental data in validation process, a series of key parameters need to be adjusted over and over again. It spends plenty of time. Recently, artificial intelligence was widely applied in PEM fuel cell, which can improve the simulation efficiency and obtain the optimal solution. The four pictures show the general model validation process. This process requires multiple simulations. There are three major types of fuel cell losses: the activation loss, ohmic loss, and concentration loss. The sensitive factors of activation loss are reference exchange current density, activation energy, and so on. The sensitive factors of ohmic loss are proton conductivity, phase state of generated water, and electronic conductivity. The sensitive factors of concentration loss are gas diffusion coefficient corrections. In our study, their sensitive parameters are our optimization objects. The picture on the left shows the computational domain of 3D plus 1D model. We can find that the membrane, CL, and MPL in the original 3D domain are simplified in 1D domain. An extension layer is added below GDL to add source terms and operate on 1D domain. The flux in 1D domain is transformed into the source terms in 3D model by user-defined functions. The picture on the right shows the model iteration process. In the 3D model, the conservation equations are solved. After that, the scalar field distribution is obtained and substituted into 1D-dimensional model to solve gas concentration, membrane water, potential, temperature, and so on. Their data are returned to the 3D domain to update the source terms of the conservation equations. The conservation equations solved in the 3D model are in this page. There, the conservation equations degenerates into flux equations in the 1D domain. Support vector machine can get better prediction results in a small amount of data. In this section, we develop a data-driven surrogate model based on SVM. The data-driven surrogate model is implemented on MATLAB using the libSVM. This model constructs the function relationship between input and output. The input are reference exchange current density, electronic conductivity of GDL, proton conductivity correction, and current density. The output is output voltage. Because the experimental condition is pro-oxygen, the effect of concentration loss is not considered. In order to obtain the optimal output, we select 5 current density to obtain predicted voltages. The predicted values are compared with the experimental values until they are closest. The relationship can be expressed as the bottom equation. The Dmax is the maximum reciprocal of the sum of square of the difference between predicted voltage and the experimental voltage. The range of current density is 0.3 to 2.3 ampere per square centimeter. The developed surrogate model is then used as a fitness function in the stochastic optimization algorithm. It aims to find the optimal parameters affecting voltage loss. The genetic algorithm optimization toolbox is used to conduct the optimization, which is implemented in MATLAB. This figure shows the flowchart of GA in this study. According to the developed surrogate model, the fitness function is Dmax. In order to ensure the physical meaning of parameters and the accuracy of results, we need to add constraint conditions for these variables, namely that variables need to be in the range of values in this equation. A penalty time is added to the fitness function to eliminate the inappropriate individuals. The end condition of the optimization process is to reach the given maximum generation. About the results, firstly, let's look at this performance prediction. In this study, there are 100 data points in total. 70 randomly selected data points constitute the training set, and the other 30 data points constitute the test set. 4 evaluation indexes are put forward to evaluate the accuracy of surrogate model. They are root mean squared area, squared correlation coefficient, mean percentage area, and maximum percentage area. The detailed expression is in this page. In the table, we can see that the RMSE in test set is 0.0174. R square is 0.966. The mean percentage area and the maximum percentage area in test set are 1.9487% and 4.0086%. The two figures show the comparison between the surrogate model predicted output voltage and the physical model simulated output voltage. The distribution is in a satisfactory manner. These results indicate that the surrogate model has high accuracy and can be used for performance prediction. Based on the developed surrogate model, we use GA to optimize the relevant parameters. The numbers of initial population and the maximum generation are set as 200 and 1000. In the left figure, the beta fitness at the end of maximum generation are around 1618 reciprocal of volt square. Namely, the sum of square of the difference are around 0.0006 volt square. It demonstrates that the generation is appropriate. The best reference exchange current density, the best electronic conductivity of GDL, and the best proton conductivity correction are 0.35 ampere per square centimeter, 5,799 Siemens per meter, and 1. The polarization curves predicted by both the surrogate model and the physical model are compared with the experimental data. They are shown in the middle figure, and they achieve a good agreement. The maximum relative area of the output voltage is 1.98%. The optimization results can demonstrate that the effectiveness of the GA model and the accuracy of the results. There, the optimal parameters are returned to the physical model for model validation in the right figure. The simulated polarization curves and the ohmic loss are compared with the experimental data and the difference in light relative humidity. The consistency is acceptable compared with the traditional validation process. The data-driven surrogate model with GA can quickly find the optimal parameters for physical model. The proton transport largely depends on the membrane water content. In the presence of water, protons combine with water to form hydronium ions. When there is enough water in the pores, hydronium ions can be transformed in the water phase. The figures show the oxygen concentration and the membrane water content distribution in the cathode Cl. When the inlet relative humidity is 0.6, the membrane water content of cathode Cl is higher, so the proton is easier to transfer to the cathode. And the high humidity, it will consume more oxygen, and the oxygen concentration will be lower than 0.2. Their distributions also prove that the correctness of the model and the parameters. The conclusion of our work are as follows. Firstly, the R-square, the mean percentage area, and the maximum percentage area are 0.966, 1.9487%, and 4.0086% in the test set. The surrogate model has high accuracy and can be used for performance prediction. Secondly, the sum of square of the difference are 0.0006 volts square, and the maximum relative areas of the output voltage between the surrogate model prediction and the physical model simulation is 1.98%. And the third, the optimal parameters are used into the physical model for model validation, and the consistency of polarization curves between the simulation and the experiment is acceptable. The validation time is also shortened more than 10 times. In conclusion, the coupling of the 3D+1D physical model and the surrogate model will be a meaningful way to improve the efficiency of numerical simulation. At last, this work is supported by the following two foundations. Thank you for your listening. If you have any question, please ask me.